This is the fourth video in the series on fundamental physics, and I'm going to depart from the routine I've been following, which is to break down materials into everyday components and then into elements and then into protons, neutrons and electrons. And the scale has been going from a very large number of different objects and species and in nature and devices that we make, down to a much smaller number of elements, about 100 or somewhat less than 100 naturally, down to 3 protons, neutrons and electrons. Only 3 particles make up all of the elements, and those 100 or less than 100 naturally occurring elements make up all the many things that we make, from space shuttles down to pencils. I then wanted to break down into smaller particles, down to the most fundamental particles, and I plan to do that, but what I want to point out is that the numbers are decreasing, and it seems to me that the most fundamental particles would be extremely simple. And I'm going to even be assuming, or should I say conjecturing, that there's really only one type of the most fundamental particle of all. And that's what we're getting toward. But I wanted to today break away from that, because I had mentioned that protons in an accelerator such as the Large Hadron Collider, when you break down protons, you have to accelerate them to high velocity, and they're immensely dense. I used the illustration that you could not pick up a very small speck the size of a grain of salt of if it were solid, if it were protons, because you would have so many protons there, perhaps 1 million, whereas the largest element has in the order of 100 naturally occurring uranium with 92, and then plutonium with 94. Remember I said 93, that I forgot neptunium, because neptunium only lasts anyway. Neptunium-239 only lasts a few minutes, so I'd forgotten about it. Anyway, there are around about 100 protons and neutrons in, so I beg your pardon, 100 protons and about 200 or 300 protons and neutrons in the largest elements. And a proton itself is extremely dense, many times more dense than any element. And I said you couldn't pick up a speck that you could perhaps hold with your tweezers. So I'm going to explain when you accelerate protons to very high velocity, why they increase their mass. And this involves a theory that was developed by Albert Einstein in 1905, and it's called his special theory of relativity. And I'm going to go through that now. So we're into some fundamental physics already. Now, if you take an ordinary body and you accelerate it, we would usually plot the distance that the body travels from here to here in a given time. And this is the time here, t, and this is the distance, which we will call L, and the velocity determines how far it goes. This is a constant velocity, and this distance here is equal to vt, which is the velocity times time. Now, this is very basic physics, basic in the sense of how we teach physics, not fundamental at all, but it's basic in the way we teach physics. I'm going to show you what happens when you accelerate something to very high velocity. So I'm going to use the same diagram, but I'm going to redraw it so that it's allows a little more room for me. I'm going to take a proton that is in a collider, and the proton is accelerated through space. This is space or distance, and remember it's going around in circles, concentric circles in opposite directions in the collider, streams of protons. But even though they're going in circles, they're still traveling. And when we're talking about kinetic energy, the direction in which the travel occurs doesn't matter, because you square the velocity to get the kinetic energy, so the direction doesn't matter. So we're going to treat them as if they were traveling in a straight line. And we'll say that our proton goes around the collider. We're going to draw the distance. That's why I put distance rather than space. It will come back to where to the same point every time. It goes around the circle, but it's going to be traveling a distance, and the distance is important. And in the meantime, time passes. And in the same way, after a certain time, it will appear to have travelled a certain distance. And it looks like the same drawing we had just now. But there's a problem here, and that is that all matter is travelling through time. And time comes into an important position when things travel very fast. Because when they're travelling very fast, they're travelling a very, very short distance and a very long, well, they're travelling a long distance in a short time, and you have to take into account that they're moving through time. Now let's explain what movement through time is like. We are all moving through time, but because we're all moving through time together, we don't see it. It's like being on a train or an airplane. You sit next to somebody, you don't think you're moving, but you look out the window and you see you are moving. And it's like that with time. Now, in order to illustrate this, I'm going to say, let's just make movement in one direction in space, like moving my hands like this. So since I'm only moving in one direction of space, I can use another direction of space to pretend that's time. So let's pretend we're all going through time in that direction. And then as we go through time, I'm moving my hands. Now we're going through time extremely fast. I will give you the exact speed in a moment. We're going through time extremely fast. But imagine it's like being on a train or an aeroplane. As you go through along the rails or through the air on the aeroplane, when you're doing that, your hands are really maneuvering in a harmonic motion, separating from one another as you go forward, and they're forming what's called a sine or cosine curve in space, in the case of the train or aeroplane. In time, the same thing is happening. But we're going through time so much faster. We're going at the speed, or what is equivalent to the speed of light. So I'm going to have to put down here how far we have moved both the proton and ourselves, who are watching this proton, are all going through time. Now, the interesting thing about movement through time is that it's constant for everything, regardless of what movement it makes in space. When I do this, I am taking speed away from time. In other words, the momentum of time forward, I'm using that and just changing its direction. So this proton will have traveled a distance at the speed of light equal to c times t. I should make my t's here smaller, perhaps, lowercase. So this proton will have gone that distance through time, because I can't slow it down or speed it up. It has that momentum in time, but I can change the direction in which it goes by making it move through space at the same time. Now, the other interesting thing is that not only did the proton go through time, but we did too, the observer. And that's the same distance as here. So I take that distance and bring it down here, and I've got the time that we have travelled and the distance that we have travelled, which is also equal to ct. So now we have something rather strange. We are here, the proton is here, we're still the same distance from the space that we expected. In other words, if the proton ends up a certain distance away from you, it's that distance away. But the interval of time has made us move to here, and the proton move to there. Now I'm going to have to give this a different distance in the time dimension, in our time dimension that we're moving on, which is the observer's time dimension. And that I'm going to call CT with a naught or 0, I'm not sure which it is, or an O. I call it the observer's time. It's an observed time that the proton took to get from here to here. Now, Einstein, knowing this, although I don't know whether he drew a drawing like this, knowing that, said, well, if it only got to there, what happened to its momentum in time, which is constant? Well, he said, if the momentum, which we call p, is equal to the velocity times the mass, or mass times the velocity. Let me change that around. It's equal to the mass times the velocity. So if the velocity has not changed because of the momentum, then the mass, and it's gone a certain distance, then the mass must have increased and the velocity has gone down. So the momentum has not changed, so the mass has increased. So he said the mass has increased. And he gave us an equation for that. I'll give you that later. In fact, I could do it now. The ratio by which the mass must have increased is the ratio of this to this. In other words, the new mass, which we'll call m0, must be equal to the mass of the proton when it's at rest, multiplied by this increase, which is t over t0. Now, I'm going to give you the math. I'll leave that up there so you can copy it down if you want to. But the thing now is we can do some calculations, because that's a right angle, and the square on this side is equal to the sum of the squares on the other two sides. So ct squared equals vt squared plus ct naught squared, and mass is equal to the rest mass times the time of the observer divided by the time which is reduced. That's called the dilated time dilation. And the value for T naught from the theorem of Pythagoras here, T naught equals T times the square root of 1 minus the velocity squared over the speed of light squared. That's very simple. That squared plus that squared equals that squared. So you can move that around, simplify that. It's only high school math, algebra. So T naught is equal to T times the square root of 1 minus V squared over C squared. And those of you who study physics will recognize that as the Lorentz transformation equation. And since this ratio is true, the mass must also follow that equation, but it's a little different. The mass naught is equal to the mass divided by the square root of 1 minus V squared over C squared. And now we can also rearrange that. I'm not going to do it. Well, all right. I will show you how I did it. I don't know how Einstein did it, but Einstein took these equations and he came up with a change to the kinetic energy. Now, if you take that right-angled triangle on the right, where this is equal to Vt, and this is equal to Ct, right, is equal to T times I've not got it. I've forgotten it. This is equal to, I call that St, which is the apparent increased speed, because if you're navigating, I'll get this in a minute. And if you navigate on the sea or in the air, you'll know that when you're traveling through through air that's got a wind, headwind or side wind, a crosswind, or if you're on a boat in a current, that you have to consider your speed through the water or your speed through the air and compare it with your speed over the ground. It's the same kind of thing. And here, this proton, in order to get to here from where it was, here, this is CT naught, and that's CT. In order to get to here, if it had stayed with us, it would have got a free ride to here with its momentum through time. And it's like being in a boat or an airplane, letting the wind drift you, more like an air balloon. A hot air balloon, the wind will take you, and you don't have to put any energy into it. But in order to get from here to here, it has to do the same thing as a swimmer through a riptide or crossing a river with a current. It has to not only travel the distance, but it also has to combat the movement of the current, which in this case is time. So in order to get from here to here, it has to go against time and also cover the space. Now, the kinetic energy to do this, which is half ms squared, is equal to, we add the kinetic energy as vectors because you square the speed to get the velocity to get the kinetic energy. This is equal to this squared, e squared t squared, plus this here, which is equal to c squared into t minus t naught over t all squared. So that is the, again, Pythagoras, nice useful little equation that. You learn that in school, don't ever forget it. And if you now, you can now manipulate this. What you do, the way to solve this, to get the kinetic energy in a simpler form, is to substitute for T naught, substitute the ratio of the mass, which was the same I showed you as the ratio of the times, and then you expand this, and you should know that. There's your polynomial a squared minus b squared, or a squared a minus b all squared is a squared minus 2ab plus b squared, and then you'll find that this cancels out with one of the elements in there, and you get back, you find out that half ms squared, which is also, this also shows you, by the way, that you can't exceed the speed of light, because if you accelerate, by the way, this is at a constant motion at this point, you've finished the acceleration. If you accelerate the speed of light, then the body is going vertical here, not traveling through our time at all, and you can't get any faster than the speed of light. And so that's a little bit of fundamental physics for you. Thank you for watching the fourth of the fundamental physics videos.